page 432, chapter 25, wireless transmitters and receivers. In wireless communications, a transmitter converts data into electromagnetic waves intended for recovery by one or more receivers. In this chapter, we'll learn how to convert data to an EM field, and then learn how we can intercept and decode that field at remote points. Modulation. When we modulate a wireless signal, we write data onto an EM wave. We can carry out this process by varying the amplitude, the frequency, or the phase of the wave. We can also obtain a modulated signal by generating a series of multiple wave pulses and varying their duration, amplitude, or timing. The heart of a wireless signal comprises a sine wave called the carrier, whose frequency can range from a few kilohertz to many gigahertz. If we expect effective data transfer, the carrier frequency must be at least 10 times the highest frequency of the modulating signal. On-off keying. The simplest form of modulation involves on-off keying of the carrier. We can key the oscillator of a radio transmitter to send Morse code, one of the simplest known binary digital modulation modes. The duration of a Morse code dot equals the duration of one binary digit, more often called a bit. A binary digit is the smallest or shortest possible unit of data in a system whose only two states are on and off. A dash measures 3 bits in duration. The space between dots and dashes within a character equals 1 bit. The space between characters in a word equals 3 bits. The space between words equals 7 bits. Some technicians refer to the key down, full carrier, condition as mark, and the key up as no signal, condition as space. Amateur radio operators who enjoy using the Morse code send and receive it at speeds ranging from about 5 words per minute to around 60 words per minute. Frequency shift keying. We can send digital data faster and with fewer errors than Morse code will allow if we use frequency shift keying, FSK. In some FSK systems, the carrier frequency shifts between mark and space conditions, usually by a few hundred hertz or less. In other systems, a two-tone audio frequency, AF, sine wave, modulates the carrier, a mode known as audio frequency shift keying. The two most common codes used with FSK and AFSK are baudot, pronounced baudo, baudo, and ASCII, pronounced ASCII. The acronym ASCII stands for American Standard Code for Information Interchange. In radio teletype, or TTY, FSK and AFSK systems, a terminal unit, TU, converts the digital signals into electrical impulses that operate a teleprinter or display character on a computer screen. The TU also generates the signals necessary to send, or TTY, when an operator types on a keyboard. A device that sends and receives AFSK is sometimes called a modem, an acronym that stands for modulator-demodulator. A modem is basically the same as TU. Figure 25.1 is a block diagram of AFSK transmitter. The main reason, well, maybe I'll read this. Okay, 25.1, a simplified block diagram for a transmitter that uses audio frequency shift keying. At the beginning, you've got an oscillator, which goes to the modulator, and below is a two-tone oscillator. Then you have an amplifier and a power amplifier and an antenna. Okay, back to the reading. The main reason why FSK or AFSK work better than on-off keying is the fact that the space signals are identified as such, rather than existing as mere gaps in the data. A sudden noise burst in an on-off keyed signal can confuse a receiver into falsely reading a space as a mark. But when the space is positively represented by its own signal, this type of error happens less often at any given data speed. Amplitude modulation. An AF voice signal has frequencies mostly in the range between 300 Hz and 300 kHz. We can modulate some characteristic of an RF carrier with an AF voice waveform, thereby transmitting the voice information over the airwaves. Figure 25.2 shows a simple circuit for obtaining amplitude modulation, AM. We can imagine this circuit as an RF amplifier for the carrier with the instantaneous gain dependent on the instantaneous audio input amplitude. We can also think of the circuit as a mixer that combines the RF carrier and audio signals to produce sum and difference signals above and below the carrier frequency. Okay, so I've gone over to page 434. At the top is 25-2, an amplitude modulator using an NPN bipolar transistor. That is worth pausing and just studying. I don't know how well I can describe it. Okay, continuing the reading, under the heading Amplitude Modulation on page 433, the second paragraph, the circuit shown in figure 25.2 performs well as long as we don't let the AF input amplitude become too great. If we inject too much audio, we get distortion, nonlinearity in the transistor, resulting in degraded intelligibility, understandability, reduced circuit efficiency, ratio of useful power output to DC power input, and excessive output signal bandwidth, the difference between the highest and lowest component frequencies. We can express the modulation extent as a percentage ranging from 0% representing an unmodulated carrier to 100% representing the maximum possible modulation we can get without distortion. If we decrease the modulation beyond 100%, we observe the same problems as we do when we apply excessive AF input to a modulator circuit, such as the one shown in figure 25.2. In an AM signal that's modulated at 100%, we find that a third of the signal power conveys the data, while the carrier wave consumes the other 2/3 of the power. Okay, page 434. Continuing the reading. Figure 25.3 shows a spectral display of an AM voice radio signal. The horizontal scale is calibrated in increments of 1 kHz per division. Each vertical division represents 3 decibels of change in signal strength. The maximum reference amplitude equals 0 decibels relative to 1 milliwatt, abbreviated as 0 dBm. The data exists in sidebands above and below the carrier frequency. These sidebands constitute sum and difference signals produced by mixing in the modulator circuit between the audio and the carrier. The RF energy between 3 kHz and the carrier frequency is called the lower sideband, LSB. The RF energy from the carrier frequency to plus 3 kHz is called the upper sideband. The signal bandwidth equals the difference between the maximum and minimum sideband frequencies. In an AM signal, the bandwidth equals twice the highest audio modulating frequency. Page 435. In the example of figure 25.3, all the AF voice energy exists at or below 3 kHz, so the signal bandwidth equals 6 kHz, typical of AM voice communications. In standard AM broadcasting, where music is transmitted along with voices, the AF energy is spread over a wider bandwidth, nominally 10 kHz to 20 kHz. The increased bandwidth provides for better fidelity, sound quality. Single sideband. In AM, at 100% modulation, the carrier wave consumes 2/3 of the signal power, and the sidebands exist as mirror image duplicates that, combined, employ only 1/3 of the signal power. These properties make AM inefficient and needlessly redundant. If we could get rid of the carrier and one of the sidebands, we'd still convey all the information we want while consuming far less power. If we could get rid of the carrier and one of the sidebands, we'd still convey all the information we want while consuming far less power. Alternatively, we could get a stronger signal for a given amount of RF power. We could also reduce the signal bandwidth to a little less than half that of an AM modulated signal modulated with the same data. The resulting spectrum savings would allow us to fit more than twice as many signals into a space range or band of frequencies. During the early 20th century, communications engineers perfected a way to modify AM signals in this way. They called the resulting mode single sideband, a term which endures to this day. When we move the carrier and one of these sidebands from an AM signal, the remaining energy has a spectral display resembling figure 25.4. In this case, we eliminate the upper sideband along with the carrier, leaving only the lower sideband. We could just as well remove the lower sideband along with the carrier, leaving only the upper sideband. We can almost completely suppress the carrier in an AM signal using a balanced modulator, an amplitude modulator amplifier using two transistors with the inputs connected in push-pull and the outputs connected in parallel, as shown in figure 25.5. This arrangement cancels the carrier wave in the output signals, leaving only lower sideband and upper sideband energy. The balanced modulator produces a double sideband suppressed carrier, DS-BSC signal, often called simply double sideband. One of the sidebands can be suppressed in a subsequent circuit by a bandpass filter to obtain an SSB signal. Figure 25.4, spectral display of a typical single sideband voice communications signal, in this case lower sideband, LSB. Going back a page, there's figure 25.3, which says spectral display of a typical amplitude modulated voice communications signal. Okay, turning over to page 436. Got a diagram here that says 25.5, a balanced modulator using two NPN bipolar transistors. We connect the bases in push-pull and the collectors in parallel. Basic SSB transmitter. Figure 25.6 is a block diagram of a simple SSB transmitter. The RF amplifiers that follow any type of amplitude modulator, including a balanced modulator, must all operate in a linear manner to prevent distortion and unnecessary spreading of the signal bandwidth, a condition that some engineers and radio operators call splatter. These amplifiers generally work in Class A except for the PA, which operates in Class AB or B, or Class B. We'll never see a Class C amplifier as the PA in a SSB transmitter because Class C operation distorts any signal whose amplitude varies over a continuous range. And going back to page 436 at the bottom, there's diagram 25.6, which is a block diagram of a basic SSB transmitter. And on the left there's an oscillator, then it goes to a balanced modulator. Below that is an audio amplifier attached to a microphone. Okay, going up again to the balanced modulator, you've got a filter, an amplifier, a power amplifier, and an antenna. Okay, top of page 437, frequency modulation. In frequency modulation, FM, the instantaneous signal amplitude remains constant. The instantaneous frequency varies instead. We can get FM by applying an audio signal to the varactor diode in a voltage-controlled oscillator, VCO. Figure 25.7 shows an example of this scheme, known as reactance modulation. This circuit employs a Colpitts oscillator, but we could use any other type of oscillator and get similar results. The varying voltage across the varactor causes its capacitance to change in accordance with the audio waveform. The fluctuating capacitance causes variations of the resonant frequency of the inductance capacitance LC-tuned circuit, causing small fluctuations in the frequency generated by the oscillator. Phase modulation. We can indirectly obtain FM if we modulate the phase of the oscillator signal. When we vary the phase from instant to instant, we inevitably provoke small variations in the frequency as well. Any instantaneous phase change shows up as an instantaneous frequency change and vice versa. When we employ phase modulation, PM, we must process the audio signal before we apply it to the modulator, adjusting the frequency response of the audio amplifiers. Otherwise, the signals will sound muffled when we listen to it in a receiver designed for ordinary FM. Deviation for FM and PM. In an FM or PM signal, we can quantify the maximum extent to which the instantaneous carrier frequency differs from the unmodulated carrier frequency in terms of a parameter called deviation. For most FM and PM voice transmitters, the deviation is standardized at plus or minus 5 kHz. We call this mode narrowband FM, NBFM. The bandwidth of an NBFM signal roughly equals that of an AM signal containing the same modulating information. In FM, hi-fi music broadcasting, and in some other applications, the deviation exceeds plus or minus 5 kHz, giving us a mode called wideband FM, WBFM. Okay, before I go over to the next page, there's a diagram here, 25.7, generation of a frequency modulated signal by employing reactance modulation in a Colpitts oscillator. We can modify other oscillator types in a similar way. Okay, continuing the reading. On the top of 438, the deviation obtainable with FM is greater for a given oscillator frequency than the deviation that we get with PM. However, we can increase the deviation of any FM or PM signal with the help of a frequency multiplier. When the signal passes through a frequency multiplier, the deviation gets multiplied along with the carrier frequency. The deviation in the final output should equal the highest modulating audio frequency if we expect optimum audio fidelity. Therefore, plus or minus 5 kHz is more than enough deviation for voice communications. For music, a deviation of plus or minus 15 kHz or plus or minus 20 kHz is required for good reproduction. And I think I'm going to stop it there because that's just, I don't understand any of it.